Um, so, what you're seeing now is how real science operates. The beginning of 15 minutes is always on connectors and cables. Okay. No, that's not working, but it's fine. This is a piece of performance art, really. We could easily get this to work, but on purpose, we're showing you what happens when we have tools that are not working right. So it is fine. Today, what am I here for? I want to tell you a little bit something about the excitement about doing science, especially in the modern times, as opposed to what you hear about in textbooks. And at the beginning, I apologize if it sounds like an old man giving you some kind of old man advice, but that's what happens. You eventually become old and you feel like you have to give advice. So that's what I'm doing at the beginning, but there will be some excitement if you hold on for 20 minutes, it will get more exciting. So the first thing, this title, Miseducation of Young Scientists, I know not everybody here is a scientist or wants to be, but it's not really that important whether we're talking about science or something, but it's more about how should you be educated on what's the right approach to take if you want to go into something which is a creative field or something where discovery is important. And I have some thoughts that I want to go over. I'm just giving you a little bit of overview of some of the points I wanted to get into, and hopefully we get into all of these by the end. So the first thing I thought about telling you about is the scientific method, or the scientific hypothesis method. And this is something that we are taught in schools. As I'm saying this, I have to say, you may think that I understand your schooling system, but not really. I'm just an American person. And so all my life, I've just learned the education system over there, but I'm talking as if I understand what you've learned, but I'm assuming some of this is kind of universal. So we understand this thing. There's a scientific method, and what does it tell us, really? The basics of the scientific method is you have a hypothesis, you have a great idea, you write it down on paper, you tell people, go out and test my hypothesis, and then hypothesis is true or false, you do some adjustments, and then if you're a genius, I mean, you're all in this genius program, so you'll have one of these events. And then you can go and collect your Nobel Prize because you're a genius and your hypothesis was right. And you thought about the universe deeply in your mind and you just came up with the right answer. And that's a little bit like what we are taught in school. Hypothesis, you test, and that's it. And that is the flow of science. In my experience, it's not like this. There is no way that you can learn about nature, the universe, the natural world, by sitting quietly in your classroom or your office and thinking deeply. This is just the kind of thing which you hear stories about, but they're not true. There's no truth to that. This is a little bit more like a real story. You start off, and for some reason, due to some technology or new concept, you observe the universe in a new way, either using a new instrument or some clever algorithm, or you're just a genius. And so you thought about some new idea and you said, well, I'll point my telescope in this direction, or I'll look with this color, or I will listen in this direction. And then step two is, if you do it right and you're truly doing something different, there's a chance of finding a surprise. And so you find a surprise, and then comes the effort of trying to convince the rest of the world that something has really happened, something new has happened, and you have to get people to believe. And if you succeed, meaning you've looked at something, you found something different, and it withstood the test of time, then what happens? Well, the universe doesn't care. Nature doesn't care that we have a new explanation or a new discovery. But the main point is that tomorrow, the story that you tell people, why is the universe here, what are we made of, the story is getting a little bit better. And that's essentially the progress of science, is that over time you find bit by bit, brick by brick, you're able to build a better story of how things work and what's going on. So some caveats to these things. uh, it's extremely difficult to not fool yourself, I find. So a standard thing that happens to myself and people that I work with is we rush into somebody's office and say, I have a great idea. I had a dream last night, or this morning this was happening while I was eating breakfast, and I had this new idea. And as long as it's just you talking to yourself, it's very easy to fool yourself that this is a great idea. But really, you're the best person in the world at fooling yourself because you know the kinds of things that you want to believe. So that's a danger. You have to be careful that it's not just you. The other thing is that I find throughout my career, very often I think I have a great idea, and then if I go to the library, I find out it is a great idea. It's just someone had that great idea already 45 years ago. So it doesn't mean I'm not a genius. It just means someone was a genius before I was a genius. And so that is good. It's good to know that it was done before and not to repeat again. And the third one is the toughest one, and I think I don't know if it ever gets easier. It's not easier for me. But when that time comes and you have a beautiful idea or a technique or a procedure or a measurement, you've discovered something, you think it's really great, it's very difficult to let it go. And you announce something to the world like, oh, I've discovered signs of intelligent alien life on this different planet using my great new telescope. And then someone comes along and says, well, I also looked there, it's not really there. At that time, you have a choice to make. Either you can say, thank you for your criticism, thank you for teaching me how I should look at things, or you can fight with that person and have a big argument about who's right and who's wrong and that sort of thing. And so this is the third thing I would say. You have to learn how to let go and say, sure, it was a beautiful idea, let's write it down, we'll put it outside, light a fire, and have a celebration about how great of an idea it was. But then let's move on with our lives and do something new. And that's maybe the hardest thing. So just to illustrate these points, how discoveries happen, how do we learn about the universe, I want to tell you a little bit of a history lesson or my perspective on the story of how gravity is being studied, and in particular how black holes and the idea of warp space and all of these science fiction concepts are happening in the modern world. So there's a story of gravity. Here we have the usual thing. We have Newton's law. This is a quiz question. How many Newton's laws do you know about? And let's say, if you think the answer is 2, raise your hand. Is it 4? Is it just 1? Everyone believes in 3. Oh, this is so great. I love it when people have the wrong answers. There's no 3. 3 is just a thing you learn in school because your teachers like to teach you more things. This is the only Newton's law that there is. Force is equal to mass times acceleration. And everything else, object in motion, stage in motion, all of those things, it's just this law stated in a different way. So really, there's just this thing. There's this other thing, however. There's Newton's maybe 4th law of universal gravitation. And what this tells us is that the attractive force, F, between 2 objects goes like how heavy are the objects, their masses, divided by the square of the distance between them. And this law, basically by itself, allows you to predict almost everything that's going on in the night sky. All of the orbits of the planets, meteors, asteroids, our orbit around the sun, everything explained by this Newton's law. And using this law, Newton was able to rederive all of the observations of the previous astronomers from the previous centuries. And that is great. Around the year 1850, so maybe 170 years ago, there were 2 remaining mysteries in astronomy. And one of them was this. The orbit of Mercury, the planet closest to the sun, was anomalous. And not anomalous that you would notice if you just looked by eye, but if you're extremely careful and you recorded it over decades and decades, you would notice the orbit of Mercury is not explained by Newton's law of gravity. Mystery number 1. Mystery number 2 is maybe less well known. At that time, 170 years ago, there were not that many planets. How many planets are in our solar system? You can just shout any number you want. 8. Okay, that's reasonable. At this time, there were 7, and the 8th one had not yet been found. But there were anomalies. People looked at the outer planets, Jupiter, Saturn, and these type of things, and said something doesn't quite make sense. If we use this Newton's law and track the orbit of these planets, there's a little fluctuation going on. Something else is going on. Something needs to be done. And what was it? We'll first look at the outer planets. So you know this equation now, F is equal to something 1 divided by r squared. And using this, you can compute what is the force on all the planets due to the sun. And then given that acceleration, you can then say, okay, it moves like this. However, you have to think about what is the effect of the gravity of every planet on every other planet. So if you have 8 planets, you have something like 64 different forces to compute. Pre-computer, pre-calculator, anything. This is just by hand. And so using very complicated algebra, people noticed, well, one thing that could explain this outer planet's behavior is if there is an extra planet out there. And so there was the greatest orbital calculation person who ever lived, Leverrier, I think in France, who said, yes, I can do it. I've done all these calculations. And if you point your telescope in the direction in which my mathematics tells you to point, you'll find a new planet. And for the first time someone did this, they did this prediction based on very complicated algebra. And within 1 degree, they found this new planet. So it was a huge achievement for theoretical and mathematical physics that you could use just pure algebra and predict where new things in the night sky would be. Amazing, I thought. How can that happen? We'll come back to Leverrier and what went on with that story next. But I just want to move on and tell you the next phase of the history, which has to do with the notion of relativity. How many people have heard about relativity and Einstein? Okay, good. I just want to say, almost nobody knows really what is relativity. We sort of know there's this Einstein person and relativity has something to do with it. And there's some equations. You can learn some equations, but what does it really mean is something that people keep on struggling with all of their lives. So if relativity bothers you, you find it non-intuitive, that's fine. I'll just tell you, it's just us here. So I can admit this thing to you. But when I first read about relativity, I looked through this book, I looked at these equations, and I said, well, this is all nonsense. Who is this Einstein person, and what is with this relativity? This cannot be how the world really works. He's talking about things that are really absurd. The speed of light is the same and things like that. And so I said, I know what I'll do. I will go into physics as a career, and I'll show the world that this Einstein person was wrong. Anyway, I'm still at it. I've never given up. And it's been something like 30 years since I read that book, but so far, Einstein is fine. But it doesn't mean he's going to be fine forever. And so it's me and him. We're still competing after all these years. One of the main things I want to tell you about today is this cute toy, which is called the laser interferometer. People have seen lasers. I think you see I have this laser pointer. What is a laser, really? There's no hand raising in this. You just shout.
It's a type of light which is converts into a thin point and then projected.
If I average all of your answers, it's actually perfect. Within this crowd, you have all of the knowledge of laser beams. It's a thin beam. It's very bright. It's one color. It's not a mix. What else do you know about it?
It travels long distance.
Excellent. I was about to say the same thing. It travels long distances, right? And if you shoot it, let's not say that, or else I won't be able to use this pointer. If you have a flashlight or torch, something like that, you point it into the night sky, it spreads all over the place. But if you shoot a laser beam, it's very narrow for a long distance. Why is that? What's so special about the light from this thing that is not there in your phone flashlight? Yeah, okay. That is a topic we'll come to later on. Maybe. I'll give you 50% for that. Yeah,
The focusing point is like small.
it is, but even if you focused a light bulb, you would never get it to go in a straight line like this. And we'll see in a second why I said that. Anyway, this tool, the laser, is used in a thing called interferometer, and I'll describe to you what that is. But this precise tool for measuring space and time and speed is really the key to the whole of relativity, black holes, the universe is expanding, all of these things. So do people know who's this person? Can you recognize that person? It's fine if you don't. This is Richard Feynman, who's maybe one of the greatest physics researchers, but then also physics educators of the past century. And his lectures on physics are probably the most popular physics books of all time. And someone asked him a question before he died, and they said, imagine the civilization is wiped out as we know it, human civilization. And then after thousands of years, it grows again. What if you could have a time capsule and you give them one message to the next civilization, what would it be? And his answer was this: everything is made of atoms. And also explaining that atoms are the smallest unit. But just with that one phrase, everything is made of atoms, he felt you could then reconstruct all of modern science and get to physics, chemistry, biology, all of those things. And then there's me. I'm not as famous as Richard Feynman. But I think actually everything is just made of waves. And today, everything I'm going to describe to you is the concept of waves. And they make up everything, even atoms. Go ahead.
That is efficient because when it's atoms, it has to have a kind of, it has to have a dimension. When it's wave, it's just a disturbance. So you can actually use waves in a better way than you can use atoms.
All right. I like your answer, 75%. Very good. Okay, I want to move on to tell you a little bit about why waves. So this is a picture of some waves interference. And if you see what's happening here, there's a pebble which was dropped in the center here. And then off the screen, some other pebble was dropped. And the wave fronts from the two waves are interfering here, or something like that. And the concepts which are very important for us is these two: constructive interference and destructive interference. So constructive interference, you see this thing. You hear this whine of the audio system a little bit while I'm talking. And what is happening there? That's called constructive interference. When my voice exceeds a certain threshold, you hear it echoing because these speakers are playing back into this microphone and they're adding to the sound wave, which is my voice. And that gives a little bit of this excess ringing. And what it does is it amplifies things. And that's because whenever this wave is going up, this wave is also going up. And so we say constructive interference, meaning they're interfering in a way which constructs something. Destructive interference, this is the opposite. So this wave is going up, this one is going down. And if you perfectly line them up, you'll get absolutely nothing. The two waves mathematically cancel out. And the precision to which you can cancel waves like this is something like 1 part in 100 billion or something like that. It's an incredible number. I wonder though, these are water waves, these are some mathematical waves. What are some kinds of waves that you see in nature besides these things? Sound waves, that's, I just told you sound waves, that doesn't count. Mechanical waves. What kind of mechanical waves? Oh, radio waves, mechanical waves. Transverse waves are waves. Oh, water waves are already here. Light, okay. That's also for free. This is light. Gravitational waves, good ones. My favorite. Microwaves are also waves. So everything which is like microwaves, gamma rays, X-rays, radio waves, infrared, all of these things are the same kind of wave, electromagnetic wave. And they're described by electricity and magnetism, basically.
I would like to describe them as short-range waves and long-range waves.
Okay. I like that. There's also strange waves, like waves in the ground, waves inside of the earth, waves in the atmosphere. But essentially, nature is made out of waves. And understanding how things move in nature, how signals move around, how objects move around, this all has to do with the study of waves. And so if you're taking your physics courses, when you get to the part about the The most boring topic in physics. What is the most boring topic in physics? It's the inclined plane. The inclined plane is the worst. I don't know what happens here, but in America, if you're interested in physics, immediately they give you the worst topics. They give you a block with another block, and then there's a spring which is half broken and a mass, and they say, would you like to be excited about physics? Here is the worst topics anymore. But instead, we do it in the opposite way. Yeah, inclined plane is one of those things. But all of these things can be understood really simply if you understand this mass on the spring or this simple pendulum really well. They're very basic things. It's not anything complicated. There's no quantum mechanics or black holes. But everything, once you start learning about lasers, the internal physics of black holes, what you learn at the end is all of these things are mathematically very similar to the mass and the spring. Nothing is like the inclined plane. You don't have to learn that. I'm a physics professor, I'm telling you. I've never had any purpose. I've taught about inclined planes for years, and I regret it. I apologize to you on behalf of the physics community. Okay, no inclined planes. Instead, I'm going to tell you about what is this laser interferometer. And this is a little bit of a historical thing. I put a heart next to this person. This is Albert Michelson. He's one of my heroes of physics. And Michelson has done measurements pre-1900, which I think I still could not replicate today using all of my modern technology. And he's just such an incredible experimentalist that I wonder if we had more people like that, what kind of truths could we really pull from nature? So what people thought pre-1887, I would say, is, well, we have water waves. Water waves, it's the waving of water, molecules going up and down. We have sound waves. Sound waves are pressure waves. So I'm speaking to you, it's not a transverse wave. Sound waves are longitudinal waves. So as I talk in this direction, and my voice propagates, there are regions of the air which are less dense and more dense. And so the density fluctuates, it vibrates the hairs in your ear, and then you hear something. And so people said the same thing for light. They said, well, light also has to have something. What is waving when there's a light wave? For everything else that you mentioned, water waves, gravitational waves, plasma waves, waves on a string, waves in musical instruments, there's always a medium, right? Something is waving. So what is waving when it comes to light waves or infrared or radio waves? No, you answered too much already. You paused for 5 minutes. Your answers are too good. I have to build up some suspense. If you answer everything, you're going to give away the thing. Like, wait till the end. You know the answer already. Anybody else? What is waving? You can just shout. I say it one at a time. Yeah, that's right. Right. People said there must be another medium. And they said, the universe is filled with this fluid thing. We don't know what it is, and no one has ever observed it. But everything needs something to wave. Even light needs something to wave. So let's say there's something called the ether. And it just fills all of space. And the light is waving through it. And so it makes sense. If the light is coming to us from this direction, and we head in this direction with respect to the ether, we should see the speed of light be more, because we see more oscillations pass us if we're going in this direction. And if we go in this direction, we would see the speed of light to be less, because we're moving along the direction of the light. And so it's similar when you hear police sirens or these type of things. As they're coming toward you, the pitch of the sound is higher. The frequency is higher because the source is coming toward you. And as it's going away from you, the pitch is going away from you. So there is this velocity-dependent effect on the sounds that you hear. And people thought maybe there's something like this also for light. Maybe we'll see something. So they built this machine, which is now called the Michelson-Morley laser interferometer. And you see what's happening. There's a laser like this, except, no, it's 1887. There's no lasers. What do they do instead? They have a sodium lamp. So it's like lights that you see outside on the streets, just these orange lights. So they take one of these orange sodium lights, they make a small hole, so it looks like a laser a bit. It's a narrow beam that comes out, but it's not a laser. It diffracts all over the place. And they put it through this mirror, and it allows 50% of the light to go through, and 50% goes this way. And the two beams come back together, and they have this eyepiece. So then they look with their eye, and they see what's happening. And this is a little bit more modern of a system, so you see there's a pattern. And the pattern which is there is very similar to this pattern. It's an interference pattern. And if you look more carefully at this image, you'll see this constructive and destructive interference. So this central wave is coming out like this, and this wave is going out like this. And wherever the waves are constructively interfering, you see these white lines. And wherever it's destructively interfering, you see these darker patches like this. And it's a very regular grid, because these waves are at a very regular wavelength. The same thing is going on in the Michelson-Morley experiment. The two laser beams come in, there is this interference pattern. But with the water waves, the wavelength is maybe millimeters or centimeters. And with laser light, the wavelength is maybe 1,000th of a millimeter or less, something like this. So it's a much more precise instrument. So they built a thing like this, and they put it on a solid thing, and they floated on a pool of mercury. Don't try this at home. Mercury is poisonous. I don't know. I mean, they didn't know these things back then, so they had it. And they rotated this thing, and they waited as the Earth spins around. They said, if the fluid is filling all of the space, and if the Earth is going around the sun at something like 30 kilometers per second, we should see as night switches today, sometimes we're going into the ether, and sometimes we are going away from the ether. So we should see a fluctuation in this interference pattern, which has to do with the day-night cycle. And they looked. They spent 6 years. They did the first experiment. They found nothing. They did it again. They found nothing. Michelson eventually wrote a thing that said, very politely, he said, there's no ether, just forget it. It's over. Morley continued maybe for a few more decades, but the sensitivity of their instrument was something like 100 times better than what you would need to rule out the ether. So they proved unambiguously that there is no ether, and that light travels through empty space. And furthermore, the velocity of light that you measure has nothing to do with the speed at which you're going. If I shoot this light in that direction, it goes in that direction at 300,000 kilometers per second. And even if I were to run in that direction, I'm very fast. You can't tell by looking at me. I'm extremely fast. I might run at 200 kilometers per second. What if I run at 200,000 kilometers per second? It doesn't matter. For me, the speed of light will be the same as it is for you who are sitting down. And this is an amazing piece of very non-intuitive science. And nobody really believed this. Many people before Einstein had a lot of the mathematics which explained relativity, but no one before him actually said, it's not just mathematics, this is actually how the world is. The speed of light is the same for anybody, independent of who you are and how fast you're moving. And that's the thing that really troubled me when I was your age. I just found it to be such an illogical statement. How could it be? But that was the point of the Michelson-Morley experiment. Now back to the mystery of the precessing planet. Yeah. Oh. Are you a pro-ether person?
Sir, I'm asking a doubt.
Okay, go ahead.
Sir, like all the light that's emitted, we know that it travels at speed, but since a lot of light is emitted through various sources throughout the universe, how does it dissipate? Like, how does it come to an end?
Oh, I like that question. Did everybody hear that question? The question was, everything in the universe is emitting light, and why is it, you're basically saying, like, why is the night sky not so bright? Because the light from everything would be coming to us all the time, right? Yeah. That's a super interesting question. This, in physics, this is called Olber's paradox, where people said, well, if the universe is infinite, and the stars have been burning for a long time, then any place in the sky that I look, there will be some light from some star, and it'll be coming toward us. And so the night sky should be bright, not dark. And does anybody know about this paradox? What is the resolution of this thing? Exactly. You were all geniuses here. I don't even understand, like this kind of question is when I was in physics graduate school, this was considered like a graduate school level question. What is the resolution of Olber's paradox? So you already know it. You have no reason to go to university. Just skip right to research. But it is basically what she said, that the universe is actually finite. It's not infinite. And then the energy is conserved. So if you emit 1 watt of light here, it has to spread in all directions. And by the time it gets to a long distance, it's just very dim. It's not that it doesn't exist, it's just the intensity is less. So numerically, that's the resolution of the paradox. Anyway, let me get, this one is a little bit more, oh, go ahead.
So I actually had this doubt when I was watching the movie Flash.
Yeah,
So Flash can like move faster than the speed of light. For him, so when he does that, time is compressed and he experiences the same amount of time and everything has to slow down.
yeah.
If we were to make a body that moves at the speed of light, the same thing happens.
Yeah, it's a very good question. When I was your age, I struggled with the physics of both Flash and Superman. Because if you look at how they travel, I love this question. It's a great question. Because, and physicists don't like this question that much. Either they would ignore you because they haven't read Flash. I've been reading Flash since like 40 years or something. So I'm an expert on all of the physics of Flash. The main problem is his uniform would burn up, right? You cannot travel at the speed of light with regular clothes. But what they exploit, I think, is the fact that it's well known in physics that you cannot start from 0 speed and approach the speed of light from 0. There's nothing to prevent you from going faster than the speed of light if you have always been going faster than the speed of light. But it's just the barrier can't be crossed. And so the secret of the Flash is he taps into a extra spatial dimension. He goes into it. It's beyond our normal physics, basically. But there is a physics explanation for it. Yeah.
So why is the fact that the speed of light is slowed down true? Why is it so?
Why is it true? Let's wait till the end for that. It's a very good question, but it takes me maybe 5 or 10 minutes to explain. Okay. So back to this precessing planet. This will tie into the speed of light issue, I think. So this is actually a very long story, but I've compressed it here for your edification. So anyway, this is going on. Leverrier has solved the problem with Neptune and found Neptune. After a long time, people have noticed what I said. There is an anomaly in the orbit of Mercury. Mercury is doing something a little bit strange. And they said, well, what do we do when orbits are strange? Let's talk to somebody who knows about orbits. They asked this person again, Leverrier, they said, please, you explain Neptune to us, please explain Mercury. And he said, well, last time there was a missing planet. Let's say there's another missing planet. But if it's going to affect Mercury, where would it be? He said, well, maybe around the sun, there's a dark planet, or on the other side of the sun, there's another dark planet, and maybe that affects things. Anyway, some other things. The summary, the other astronomers said, well, no, not really. Actually, there's nothing out there. And so the mystery remained from roughly 1850 until 1910 or 1915. And that's when Einstein comes back on the scene. So this is actually the effect. This is the orbit of Mercury. And this place where Mercury gets closest to the sun is called perihelion, which means closest distance to the sun. And the orbit, if you watch it over many centuries, maybe 1 century or so, you'll see that Mercury does like this, and there's this pattern, and the orbit precesses over time. And almost all of that effect comes from these other planets, Venus, Earth, Mars, and those kinds of things. But if you're very careful with your algebra, you take into account all of those effects, and then you find that even taking into account the whole solar system, and that is really intense algebra, pre-computer time, only 90% is explained by Newton's gravity. And so there is still a 10% anomaly nobody can explain. And then finally, Einstein shows up in 1915. And Einstein, this is a part of the story which people don't know generally, but I'm telling this to you. It may sound like I'm attacking Einstein or something like that. Who am I to attack Einstein? I'm not. I'm just telling you a story. So 1911, Einstein says, hey, Special relativity is solved, the speed of light, blah, 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 trains, flashlights, all of these things. Now I got something new. I've been sitting in my office and working for several years. I have a new theory of gravity, and I can explain why Mercury is going like this. And it's because gravity is not really Newton's gravity. It's the new gravity. And then as new gravity, space is actually warped in a different way than what you would expect from Newton. And the astronomer said, wow, Einstein, we all know that name, smart. Einstein means genius, right? Let's go do what he says. And Einstein said, go look at some stars. And the astronomer said, fine. Whenever there's a solar eclipse, the sun is blocked out, so we can observe the stars that are very close to the sun. And if space is warped, then when that starlight comes to us from behind the sun, it will get bent, because the light that passes close to the sun will get bent by the curvature of space. And so the sun acts like a gravitational lens for the distant stars. So fine. They said, when are the eclipses? Let's go find them. So 1912, total solar eclipse. Everyone gets their things, they travel to South America, and it rains. Rains the entire time. People are there and their telescopes get wet, nothing. 1914, they said, this is it. This is the real time. So they get all their telescopes. Where do they go? They go to the Crimea, which recently invaded by Russia. Same thing was happening in 1914. Russia was always in the Crimea. They went in there with their telescopes. The Russians arrested them and put them in jail. And they said, that's what you get for doing astronomy in the middle of a war. Lucky for Einstein, none of this worked out. In 1915, Einstein said, hey, it's me again. I have another theory of gravity. And this time, the deflection of light will be this many degrees instead of this many degrees. There was a factor of 2, it turns out. And that's what he figured out. Okay, Eddington says, okay, let's do it for real this time. So now there's an expedition that goes to South America, there's one that goes to Africa. They wait for the eclipse, and what is predicted is what happens. They look at the images, and the stars that are very close to the edge of the sun, where the eclipse happens, they move by this amount. And the closer they are to the sun, the more that the light bends. And so, aha, it's proven, and Einstein becomes famous, and his pictures everywhere, and now you all know his name. And it's for this thing, that he predicted a change to the theory of gravity. Now, I want you to just pause here for a second and see what does this all mean? You have this idea that Einstein sits alone in his patent office, in his office or something, and does a bunch of equations and predicts how things work. But it's not really like that. People observe the natural world very, very carefully, and over time the technology gets better so that your observations get more and more sharp. And eventually, there's too much tension. You're confronted with the fact that your idea for the world and nature is just wrong. And it's too bad. It's too bad that your ideas are disproven by nature. But when that happens, nature always wins. And so when that happens, that's when the new theory comes in. It's driven to be created by observations about the natural world. And that's the true story of Einstein's relativity. I'm not a equations physicist. I'm more like a person who, like I have my lasers, I shoot things with lasers, I do experiments. And so there won't be many equations here. I'm just giving you this one equation because I think it's good for you to see what is the big deal with Einstein's equations. You don't need to solve them, but I just want to describe to you what it really means. And so the great successor to Einstein, John Wheeler, said, what does relativity really mean? He said, space-time, meaning the curvature of space, tells matter in which direction to move. Meaning, like if you're in the space-time of the sun, then you orbit the sun, that kind of thing. And the matter and energy also, which is there, the more matter and energy that you have, the more curvature of space-time that you get. This thing, nobody asked for this, but this has recently popped into our equations. And I'm sorry, but it's not my fault. It spoils the beauty of relativity, but that seems to be how nature is. That's it for my history. I'm not going to move on to a little bit more exciting topics and tell you about some modern things that are going on. Black holes. Black holes are a topic of great mystery. We still don't understand them. It's amazing to me that they really exist and have been found in nature. If you'd like to get more into them, I'm not going to go into all of the details of them, but there's plenty of resources on YouTube. So I like this one. It's a good overview of all the different features of black holes, and you can dive deeper into them. And they're this YouTuber channel, Domain of Science. Okay, so what do we have now? Einstein, 1915, he says this is relativity, space is curved, this is the explanation for gravity, everything is now solved about mechanics, there's nothing left. In 1916, he says, aha, not only is space curved, but now if you do things, if things are vibrating, then those vibrations curve space, and those vibrations propagate away as waves. Just like if you take a magnet or something with electric charges and you shake it like this, it produces electromagnetic radiation. And in fact, laser light, like this thing, is produced by the oscillations of atoms within this semiconductor. And he said the same thing. So there's gravitational waves. In 1918, he says, okay, well, this thing wasn't quite right, but now this is the correct paper. Oh, also there was a factor of 2. I am not telling you this to say, oh, look at Einstein, he made a mistake. I am just saying, this is it. Like the bane of all science is it a plus sign or a minus sign? I don't know. We just use whatever works. And then this thing, factors of 2 and pi are always showing up in our equations. Let's forgive him. Eddington, who was a great astronomer at the time, super famous, especially because of this eclipse expedition, said, no, I don't think so. I think this is just all in your mind. And Einstein says, well, I don't think it's in my mind, but they're too tiny. Gravitational waves will never be detected ever, ever, ever. And I'm not sure if they're real, really. Maybe 20 years afterwards, after Einstein's death, a student, Pirani, comes up and says, well, actually, they're real, and mathematically I can show you. And as soon as that happens, all of the experimental physics community says, oh, really? You think we can't measure this? We'll show you. In 10 years, we'll measure this thing. And so they got started around 1960. And it only took 55 years from them saying, let's do this, to where the first detection happened. Just 55 years. Not that bad, I would say, considering how things go. And this is what happened. So in September of 2015, a signal came to us from outer space. It was a merger of 2 black holes 700 million years ago. 700 million years ago, so who knows what was happening on the Earth that long ago. But these things merged. And in September of 2015, I was working on my project, which was to detect these gravitational waves. We had finished working for the evening. People had some discussion, should we leave the instruments running, should we not? Luckily, the people who were working there late at night after midnight said, yeah, sure, let's press the on button before we go home for sleep. Nothing will happen, we've never detected anything, but maybe we'll get some diagnostics, what's wrong with our machine? And that night, this signal came in, and it is so far still the biggest signal we have ever found. And it was surprising for us, because I had not been waiting for 55 years. I'm not that old. I look old. I'm not 55. I had only been waiting for 20 years or something at that point. But there's others who had been waiting for something like 45 years for something to happen. And after this happened, there was a Nobel Prize awarded to 3 of my mentors and a lot of front page news, a lot of excitement for this discovery, and even a Hollywood movie, Interstellar, was made about black holes and relativity. But it was a big surprise. I think before 2016, everyone said, your instrument, this LIGO instrument, is a neutron star detection machine. What's a neutron star? It doesn't matter what's a neutron star. It's just another kind of thing in space that can smash together. People knew about neutron stars and said, those things are smashing all over the place. You're going to find neutron stars all day and nothing else. After 2017, the detection, everyone said, wow, I guess there's not a lot of neutron stars out there. Lucky for us, there's way more black holes colliding into each other than we thought. So although we didn't find almost any of the things that we were looking for, we did find the black holes, which we were also looking for but didn't hope for. in that kind of quantity. So great surprise for us. Yep.
Why do neutrons start radiate a kind of a streamline of radiation, which it does not
Oh.
when it continues to rotate, like any object it comes close to it will be hit by the radiation. But
Oh. Well, I'm not a neutron star expert, but the neutron star is just a very tightly packed star. It's like 10 kilometers in size. And it has a very intense magnetic field. So the magnetic field on the neutron star is maybe 1 billion times stronger than any magnet on the Earth, and which means like it will rip the iron out of your body, that kind of thing. So a magnet that strong, when it's spinning fast, makes a lot of radiation, just in the same way that a rotating object makes gravitational radiation. So very briefly, this is just the idea of how we detect these kinds of things, the waves in space. These two things are spinning. As they're spinning, the gravitational force from these things on the Earth changes slightly. And we do the same thing as what Michelson did. The laser comes in from one side. Now we have lasers instead of sodium. It goes down these two paths. And when it comes back together, we look to see how the interference changes. Destructive interference becomes constructive and that kind of thing. And the reason this happens is because the nature of gravitational waves. When there is a wave in space itself, it's not like a light wave. It's more like a sound wave or a water wave, that the medium itself is bending. And a wave of gravity is a wave in space. So space itself is stretching. What does it mean to have space itself stretching? It's not a very easy to feel, it's not a very intuitive idea. It's a thing that instead you can measure. And so we don't talk too much about what is really happening. We just say when the light goes up and down like this, if the space-time is stretched, then it takes a longer time for the light to go to the end and come back. And whether or not the wavelength of the light has been stretched, or the space has been stretched, or the time has been slowed down, that, according to relativity, really depends on your viewpoint. What is true is what you can measure. And what we measure is the interference of the light. So this device is now so sensitive that it can measure a change in the size of the Earth, which is the sort of thickness of the human air. So an extremely sensitive device. Fluctuations that it can now measure are smaller than the size of an atom, smaller than the size of a proton, maybe a million times smaller than the size of a proton. So it's an amazingly sensitive instrument, and it's difficult to really understand how can you measure anything which is smaller than an atom. This is what it looks like. This is the one where I've spent much of my life. This is in the southeastern part of the United States. It's like a very swampy, I don't know, a lot of mosquitoes. People there eat fish a lot. It's like Bengal, where my parents came from. They've traveled all across the Earth and then ended up in the same place that they started, more or less. But this place has a laser interferometer now. And this size, I want you to appreciate this thing. These dots here, these are automobiles. So a human you can almost not see. And the distance from here where the laser is down to here is 2 kilometers, and another 2 kilometers down here. So this full L-shaped thing is 4 kilometers this way and this way. And the entire system has been pumped, so there's no air left in the system. They're just empty tubes for the laser light to go. Yep.
So for even something like a bird landing on it would disturb you.
It does.
So is that just something that happens in the
Yeah.
How do you maintain it?
Well, okay, I didn't want to get into this topic, but you have forced me. When I was a student here, when you're doing your PhD, it's a lonely journey. Most of the times it's just you, and you don't know what are you doing, and is it worth anything? Does anybody care about what I'm doing? And exactly what you said happens. Sometimes you're working here, it's very sensitive, and some animal comes by and disturbs the instrument. It can be a deer, it can be a cow, dog, birds, bees, whatever. All of these things are around this system, these places. And although my area is experimental physics, the way I look at it is experimental physics has to do with the natural world. And so animals are part of the natural world, and I treat them in the same way that I treat disturbances from cosmic rays or that kind of thing. It's just part of nature. So you have to learn how to get rid of the animals, or just convince them to go some other place. And we do that. So we have methods to take care of birds and things like that. No animals are harmed, more or less. I mean, some animals are harmed, but not many animals are harmed. Not harmed by me, let's say. Okay, so inside of these places, what is there? There's super cool optics like this. This is the laser system. It looks purple. It's infrared, but if you take a picture with your camera phone, it looks purple because your sensor doesn't know how to handle it. I'm just showing you, this is actually how all of this runs. When I started, I thought I must be the youngest person. And really, there's a bunch of professionals which are doing all of this high-level science. But when you get into it really at the forefront of what's happening, all of the progress is driven by whoever is the youngest, because you have the energy. And I need a nap in the afternoon, but you can have some tea or something and just work 24 hours, I think. So whenever you get into this field, if you get into this field, don't worry, like pretty soon you'll be at the head. This here is our group of summer students who are visiting the Louisiana site. And I just want to highlight these two things. In my group at Caltech, we have a summer program for undergraduates who want to get into this field. And these are 4 from that year. These two here, Disha, who's down here from Bangalore, and Shruti, also from Bangalore, both are now doing their PhDs in this field of gravitational wave physics. Shruti is with me in California, and Disha is was in Australia, but has now just graduated. So there's a few of these detectors in the world. There's the 2 in the US, one in the Northwest, one in the Southeast, a German one, a European one called Virgo, a Japanese one called Kagra. These are both 3 kilometers long. And then finally, we have plans for building one in India. And this has just been approved last year. And so we are deep into the process of building it. The site for it here is, well, I guess it's directly south from where we are now. It's really just in the middle, north, south, east, west. It's eastern Maharashtra, I don't know, maybe 10 or 12 hours east of Mumbai. This is an artist rendering of what it would look like. The idea is that it should be identical to the US instruments, but I don't like that idea, identical to the US instruments. The US instruments are a bit old. They were installed in 2015. And you would say, have we learned nothing since that time? I mean, are we going to install really the same things that we did in 2015? No, we want some new things. We want new kinds of computing. We want AI strategies. We want new kinds of quantum mechanics and optics in our system. And so that's what we'll be doing. And you may have heard a lot about quantum mechanics and what is this all about. If you ask me, I can tell you. United Nations has declared this to be the year of the quantum. And how does that affect us, and what am I talking about here? There's 4 pillars of quantum technology, I guess. One has to do with information, quantum computing. These other 2 things you may not have heard about. Quantum measurement tells us how to go way beyond what we are doing now. We think that we can measure something smaller than the proton, and that's a great thing. But my ambition is really to go thousands of times more sensitive. I want to be detecting the black holes from the beginning of the universe, and really to find out what is going on at the Big Bang. And that's the kind of thing that we can do with some quantum technology, which will be really the heart of the next interferometers. Let me just move on. I wanted to say something about how this is done. So this is a picture of my group maybe a few years ago. And when I was posting this picture on there, I noticed this thing. Just the people in this one photograph, which is not even everyone, they're from 9 different countries. And essentially, I had to recruit from all over the world in order to get the right portfolio of skills that we needed. And it's not that these super leading edge experiments are run by a bunch of PhDs in physics, everyone's sitting around and doing relativity all the time. It's not like that. It's mostly engineers and technicians who are doing the actual work of designing and building these high precision systems, feedback systems, and so on. And we all work together. And so technicians learn from physicists, physicists learn from engineers. We all teach each other the various tricks that we need to learn. And after several years, it's not really clear who is who anymore. We just have different job titles. There are very few professors here. Professors just go around and give lectures at universities. We're not doing that much work anymore. So I just want to conclude here by saying some things. I've tried to tell you this is my feeling about how science is done. You want to remain open-minded. And just keep in mind that whatever you can do, if you really want to make some advance, you have to go deep. You cannot be superficial and just think, you know, I'll get a CS major, I'll use some AI, magic will happen. That's not how things work. You'll have to study deeply and build expertise over at least a decade in whatever area it is that you want to become an expert on. But this cartoon is about the danger of listening to experts, I would say. What we learn in school, I have a PhD, therefore I think I'm smart. I specialize even further, and my head grows larger because people tell me how smart I am. And then finally, I go around and travel the world and give advice to people because I'm so wise and I have this PhD. But really, what do we know? Like, those of you who are sort of thinking about a computer science future may know about the dangers of AI, right? You take a model, you train it on all the data that you can afford, you make the biggest model that you can, and it works pretty well in the domain in which you've run it. And then you try to extrapolate it, and then this is your face. And you say, well, what's happened? Why does it not work? I just changed one parameter. But then when that happens, you do this cycle a few times and you learn humility. Professors, however, don't. There's no fourth step. We just continue this advice giving here. So take what I'm saying with that kind of caveat too. So let's go back here. I've mainly just talked about gravity and what are we doing, gravitational waves. And I wanted to tell all of you about this LIGO India project, because to me it's the most exciting thing scientifically that's happening in the next few decades on the Earth. And the reason for this is that we've just barely opened up this window of how to use gravity to look at the universe. And we say, we'll use the gravitational radiation. All throughout the universe, black holes are merging and producing these sounds. And how would you say, like, do people understand how bats work? Bats work by echolocation, right? So bats make this sound like, and by listening to the speed at which the signal comes back to them, they can figure out the shape of the room they're in. By listening to the, the resonance time of the room they're in, they can tell a little bit about the materials. And it's a normal process in electrical engineering that you snap your fingers and you listen to the response. It tells you about where are you, what is the room you're in, what is the world that you're in. And the gravitational waves work like that for our universe. They are like, the heaviest things in the universe are smashing into each other. And when they do that, there's so much energy released that at that moment, that black hole merger, in terms of the energy that it puts out, is brighter than all the stars in the observable universe. It's an incredibly powerful thing. And that vibration propagates throughout the universe. And just like the Olbers paradox you mentioned, this gravitational wave doesn't, oh, hold on. I'm in the middle of my closing dramatic story. You can't interrupt. This is the poetry that I'm giving you. So when the black holes smash together, they make this vibration, and the vibration travels across the universe. And what we get for free, essentially, is because the black holes are constantly smashing into each other, the waves of energy from them are illuminating the universe, not with the light, but with this sound, which is the vibration of space itself. And by listening to this vibration on the Earth, essentially we are doing ultrasound of the entire universe and finding out What is the structure of space? What is the size of the universe? How old is the universe? We get all of this for free because the universe is producing these sounds for us. At the moment, we're very limited in this because the two LIGO detectors are in the US. The Earth is a sphere. You have two instruments here, and that's no good. Why? Because you want to know where these signals are coming from. And in order to find out where something is coming from, you need to triangulate. So you need 3 detectors, and you need to measure the time delay from the source and compute based on your 3 detectors where that thing is. And if you can find out where every signal is in the universe that you're hearing, then you can really compose a map of the universe. And it is really like an ultrasound map that you would get and find out what's really going on, even in the parts of the universe which are dark to us. The problem is this. Making one of these machines work is not the job of Einstein. Einstein's work is long over. Equations he gave us, we're happy to have them. But the next steps, what will happen in the next decade, I don't know. All I know is the technology that I've worked on, and I give that to you if you decide to work on this project. But all of you will have to invent something new. We've spent the last 50 years getting to this place where we're getting the first whispers of gravity from the universe, but all of these tools using AI, quantum mechanics, putting all together all the tools we have, we will finally be able to really observe what is going on in the universe. But it takes an entire crowd like this. You see, I had to recruit from 9 different countries just to get enough people to make these detectors work in the US. And I've only showed you a small group. There's really hundreds of us who make the machines work. And you need something like that. We're going to need of order 50 very talented people in India who are specialists in engineering, computer science, physics, everything. If you have a skill and you're good at it, it almost doesn't matter what is the skill. If you find something that you're passionate about, you'll be good at it because you're obsessed. You want to do it all of the time. And if you find something like that, you can be excellent. And if you can be excellent in a few things, I'm sure you can be excellent at the things that we need for this kind of project. So I'm inviting you, feel free to ask me more about it, ask others here about it. If you're interested in any of these topics, whether it be fundamental physics, engineering, mathematics, or anything, there's a place for you in this project. And the discovery space is immense. We're at the place now, technologically speaking, where quantum sensing is now being incorporated into these measurements. I didn't talk about that yet, but the next few decades will really be taking us from the essentially 20th century world of classical measurements of space into the modern era of AI-assisted quantum measurements of space-time. So we're ready, and I think in a few years you will all be old enough and you can join us. And please come to the Hingoli site and help us make this machine work. So thank you for your time.
Questions? There?
So I had 2 questions. One, in one of the slides you had mentioned about quantum measurements. So my question was that, do you think with enough time and advancements, would we be able to measure distances close to the Planck length? I mean, Planck length would be difficult, maybe slightly bigger than that, maybe 10 times or 100 times. Do you think that's possible?
So the question is basically about how small of a distance can you measure? And eventually you get to the point where if you try to measure something which is very small, you need so much energy to measure that length that you will create a black hole. So that sets an ultimate limit. I'm not worried about that limit really, but I think realistically we can get to something like within a factor of 1 million of the Planck length.
And so my last question was, one more question was that, so I read somewhere that many quantum physicists believe that all fundamental forces of nature will have a particular particle, correct? Am I correct with that? So we have found all particles for out of the 4, we found those particles for the 3 fundamental forces except gravity. So that I think makes me question whether gravity is actually a fundamental force of nature or whether it's just a combination of the other three that we see on the macro scale. So what are your thoughts on that?
Well, how do you even know about this question? This is like I would say, late at night when nobody's around, physicists talk about this kind of thing. What is really going on with gravity? Yeah, this is why I draw this diagram here. So gravity is off to the right in the red zone, because as far as we can tell, anyone who's tried to come up with a theory of gravity which involves quantum mechanics is wrong. So what we do is we come up with theories which are only a little bit wrong, and we try to use those to think about things. I think it would be amazing. I would think it would be amazing if gravity was not some sort of quantum system underneath. And I mean, again, like it's just us here secretly talking about this, so I'll tell you my opinion, which is gravity, when you think about Einsteinian gravity, it's really describing something like the flow of a fluid. Einsteinian gravity is very classical and smooth. And it's a little bit like when you think about electromagnetism. Electric fields, magnetic fields, all of these things there's no quantum anything in that. But the quantum mechanics come into that kind of thing as a way of asking what happens when you get to very strong electric fields or very tiny distances. Gravity may be a completely different kind of thing. It may be that this room, in fact, that we look at, we say this is space, we have a notion of time, space and time. All of these things may be just words that we use for some more fundamental quantum behavior. And so the very notion of space and time might just be a human invention based upon our observations of more hard to understand quantum things.
Thank you, sir. Thank you.
So, hello, sir. Firstly, I really enjoyed the talk. It was like very intriguing. All the topics discussed were really nice. So, my question is that towards the start, you had the slide where where if we could send a message back in time, then that would be that everything is made of waves. So, certain properties which apply to waves will not apply to particles and vice versa, such as the wave-particle duality that's seen in light. So if everything is made of waves, at what point does it start behaving like a particle? At what point do certain laws stop applying to it?
I like these. These are the best questions I've ever gotten in a talk, maybe. This feels a little bit like being at my like graduation exam where they asked me very tough questions. Yeah, what you're asking is a really delicate question about interpretation of quantum mechanics. And I'll just say everybody thinks they're right about this, and not everybody agrees with each other. What we know is how to do mathematics and predict what the outcome of experiments will be. And in that sense, we consider quantum mechanics to be particles and as a particle-wave duality. But fundamentally, when you look at it, there is no such thing. This is just a sort of a modern, it's a kind of anachronistic invention based upon how people thought about things 100 years ago. What we know for sure is that there is a wave equation which describes how quantum things evolve with time. And the only time when things act like particles is when the quantum system interacts with something which is larger and macroscopic, like our eyeballs or something like that. So if you sit in a dark room and there's a very dim laser beam on the far side, you can almost detect single photons on your eye, which makes you feel like it is a real particle of light that's hitting you. But really what's happening when the particle of light hits your eye is not really a particle. It's just the quantum wave interacts with the quantum waves of your eyeball, and eventually it turns into a kind of a probability that it looks like some particle hit you. And it is, the description is bad, and the description is bad because we're using English, and this is a bad language for trying to explain quantum mechanics. But in a mathematical way, it's easy to, I can describe to you how this works, but in English it's difficult because we have no words to distinguish between what is true and what we've observed. We always assume that what we observe with our senses is real reality. But I think this is just a human thing. not true.
So thank you, sir.
Sir, so my question
Is that the same phenomenon that people observed with Uranus, as in it wasn't obeying the path that people believed it would, since there were only 7 planets. That's why Verrier kind of tried to do some calculations and get the 8th planet. We also observe similar anomalies post the Kuiper belt with objects like Eris, Sedna, with highly elliptical orbits that are mostly facing towards one direction. So that's the argument for the 9th planet, right? But we still haven't seen one yet. Why is that, and could there be any other explanation for the high eccentricities of trans-Neptunian objects?
Yeah, I think so. So when essentially at the edge of the solar system, what almost everyone believes is that Newtonian gravity is accurate to describe gravity at that size of a scale. So you need the Einsteinian gravity when you're very close to the mass, because the warping of space is different from what Newton would have described, or the force is different. Almost nobody thinks that that is true when you get to large distances. So I would say 99% of scientists would say there are just other objects out there which are dark. And it doesn't mean they're special, they're just dark, like dark gray or brown or something. And there's not much light. The solar system is so large. When you go to the distance of Pluto or 5 times Pluto, something like that, it's very difficult to get any light back at all. So the fact that nothing has been directly imaged doesn't mean that it doesn't exist. I mean, if 50 more years go on and nobody finds anything and the anomaly is there, I think then we can start asking about gravitational anomalies. And there are some theories about the edge of the solar system having a different law of gravity than the inner solar system. But so far, that's very speculative.
So what would you like to define as a wave, since you referred to it in the slides that everything is a wave? So what would you define it as to be classified, to classify atoms as waves?
Yeah, so it's similar to the photon, this particle wave system. So we say that there's a photon as a particle when we have a measurement which would localize it in time or space. But it behaves like a wave when we are not observing it. And what is a wave? Just like an electromagnetic wave. So it's something that has an oscillation frequency, a wavelength, and a period, and it oscillates in space and time. And so when you think about something like a proton and a neutron, what is the difference between subatomic particles? I mean, it's not like inside they're built of different things or something like, it's something more intrinsic to them. You cannot keep reducing the system to smaller and smaller particles. And these subatomic particles, I don't know 100% the answer to your question. And that's just kind of the questions you're asking me today are like at the edge of my knowledge. But these things like protons, neutrons, they are like excitations of a more underlying force. So laser beams and things like that, we would say those are excitations of the electromagnetic field. And things like protons and neutrons are more like vibrations of the underlying force law which governs this subatomic particle thing, which are like nuclear forces and fields.
Thank you.
Mm-hmm.
So I had a couple of questions. So do you believe that the universe is finite or infinite?
Well, I don't know. I think there's an edge to the observable universe, but there can easily be a region beyond that which we haven't observed. There's another theory which thinks that there's a vaster universe, and we live in a sort of bubble universe in a landscape of many bubble universes or something like that. I just say, as an experimental scientist, I don't believe in things like this. I just say there's no information, and both are nice stories, but they're just stories until there is some evidence to discriminate between them. And in science, this is my personal feeling, but If you have made up two stories which are completely indistinguishable, I think that's not science anymore. Now you're just in the story-making world. So my answer is I don't know.
Yeah. So Einstein also proposed a theory that the black hole had a point singularity, like every black hole has a point singularity. But if we see that the black hole is constantly in motion, so is it possible that it has a point singularity? It should have a ring singularity which is also moving, right? So
Yeah,
I just
yeah.
wanted to know the answer to that question.
Yeah, I feel bad because all of these questions you're asking are too good. And so my answer is always something like, I don't know. But it can be both. So one possibility is there is a real singularity at the heart of the black hole, and then all of our existing physics doesn't work. And something new has to be invented to describe how you can have mathematical singularity. Another possibility is that gravity itself is not classical, so you cannot have this sharp ending. And that at the center of the black hole there is some fuzziness and no true singularity possible.
And so one more question, the last one. So the value of the Hubble constant is constantly changing. So can you give an exact value of that? Because it's really important in calculating the age of the universe and all.
Yeah, we would like to. So the Hubble constant maybe is a bad name for it because it's not constant, but the Hubble constant refers to how fast are things in the expanding universe, how fast are things moving apart from each other. And what we've noticed locally is that the speed of things is sort of like the Andromeda galaxy is moving away from us at something like 70 kilometers per second. And there are different measurements, but within a few percent, it's just this number, 70 kilometers per second at the distance of Andromeda. But there's nothing to worry about for our galaxy. Our galaxy will remain bound as a galaxy for billions of years. It's still unknown, I would say. 25 years ago, we found out the universe is accelerating. And I think if you look at any of the modern astronomical results, you can see that in a few years, we'll have to do a re-explanation of what is really going on in the cosmos.
Yes, sir. So I had a problem I wanted to clarify. So first things, my problem is in two parts. The first part is that for gravitation to exist, according to the law of conservation of mass, then there must be a medium for it to propagate. That is the first part. And the second part is that if light is traveling through vacuum and if the first part is proved that gravitation has a medium to propagate, then light must constantly be bent at every single point and it should not travel in a straight line but in an orbital manner. So how does light travel in a straight line and how is the first part true?
Yeah, the medium through which the gravitational waves propagate is the medium of space. So there is no extra medium. It's something, the gravitational waves are like changing the coordinate system of your plots or something like that. It's a fluctuation in your definition of what is length and time. There is no other medium besides that. And you're right, when light propagates through space, it is not really going through, it's not really a straight line. It looks like a straight line to the level that we can tell, but yeah, in fact, because the universe is always vibrating, all of space is filled with this curving, radiating gravity. So the light is always going in through a twisty path. Yeah.
It's bent at every point, it would move in an orbit and not in a straight line.
No. No. It's not that bent. It's just slightly bent. So it goes like a snake.
My question was like, so you talked about this existing notion that that space and time are usually, there's this notion that space and time are just constructs of, humans. So, and we can never reach to the true nature of reality. So,
I don't know about that part.
so do you think that quantum mechanics and relativity and all theories of physics will ever be able to explain the universe in its most true nature?
I mean, we will always explain more, but it's difficult to know, what is the ending or something. We can imagine all the best experiments in the world and measure everything. But then someone can always ask something like, why is there a universe at all? Or why are we not living in 4-dimensional space instead of 3-dimensional space, or any of those type of things. So I think very likely is that our knowledge keeps expanding. Science gets more and more difficult because the easy questions are handled more. But then our technology is getting better, mathematics are getting better. So although the problems are getting harder, humanity is getting more and more capable of solving much harder problems. The kinds of things which were a PhD project in 1985 are now like summer student project in 10 weeks. So just the capability of us is getting so much more. It's difficult to see. I think we look into the past and we say, oh, there's people like Einstein, Chandrasekhar, how can we ever compete with them? We are competing with them. It's just they're more famous. But we can be famous too.
Okay, last question.
You said that you are trying to prove that Einstein's theory of relativity is wrong, right? So I want to ask you, do you think that the theory needs to be done away with entirely, or there are only some parts that are wrong? And if you think it's wrong, do you think that it means the Einstein-Roosevelt bridge can also not exist? And if it does not exist, do you think that means that other dimensions and universe also do not exist?
Well, I think the way in which we understand the universe makes it seem as if we have 3 dimensions of space and 1 of time at the moment. Now there's a question, are there other dimensions of space? Are there other beings who live in higher dimensions of space? Are there lower dimensional creatures? Even if there's no creatures, is there an existence of objects in 4 dimensions of space or something like that? There's a way that we can test these things. And that is why I was telling you that ultrasound story, essentially. So, and it's related to the Olber's paradox. So if you have a light source and you put out so much energy, you know that the light goes into this sphere. And therefore, if you measure the energy at any point, you can compute the distance because you believe in the 3 dimensions of space. However, if you have another way to measure the distance, then you can look at the brightness and say, aha, the brightness is actually decaying faster than it would in 3 dimensions of space. So we can use these type of astronomical events to understand if different regions of the universe have different dimensions, different number of dimensions.
So I also want you to ask, like, if we somehow put light through a medium that is disfigured or distorted, right? Will it change anything about the light?
That is a deep question. I don't know. I think for sure what would happen is the brightness of the light will change, but whether the extra dimensions will change the color of the light or something is not as far as I know, but actually we haven't found these dimensions yet, so any guess is possible so far.
Thanks, sir.
You just have to design an experiment.